So I've tried to do this demo for the past 2 days, and there's always a bug that keeps coming up. So I think I'm just gonna do the whole demo. There might be bugs. If there are, please bear with me. And hopefully you're interested enough to just watch till the end. And if not, I'll understand. So we're gonna be talking about CAD and PLM systems, but maybe quickly as an introduction. There's one thing that I really like about GitHub, if we compare the world of software with the world of hardware, is that on GitHub, almost everything is automated. So you can just git push your code to GitHub and it gets automatically stored. And then you can set up some automated builds that will create all the artifacts automatically for you. And that's just a super nice experience, and it makes sure that people keep pushing their code to GitHub so that GitHub stays up to date, because it's actually super easy to do that. So if you compare this to, this is a PLM systems, for example, Innovia here, it's a very different experience. When you push something on Innovia or you try to set up a release, it's an enormous amount of work. And maybe it can be slightly easier if you use tools that are like in the Innovia tool suite, for example, CATIA or SolidWorks. But if you use any tools that are outside of this, it becomes even harder. And so it would be cool to try to figure out if we could get an experience similar to GitHub, that like in the end is like kind of platform agnostic, but for the field of hardware. And so what I was thinking of starting to focus on in trying to solve this problem is to focus on assemblies, because I think that if we can think of stable ways to generate assemblies, then we have solved the first step in creating an automated PLM system. And so if we come and look at an assembly here, so looking at this hand, you can see that I'm designing all the sections of the finger, for example, in this file. And so we have two parts. We have the end section of the finger here, and then we have the main section of the finger here. And if we go back to the assembly, the way we say where each one of those parts is going to go is that we basically set constraints between parts of the geometry of the finger. And this is extremely intuitive to use, but it's actually not that powerful, because if we start changing our geometry, and so for example, if I go here and I, for example, turn on this revolute, that's going to change how this hole here is defined. So instead of being a through hole along the y-axis, I'm going to do a revolute around the y-axis to remove material. So I'm going to turn this on right here. Oops. There we go. So I changed the way I was defining this geometry. And if we go back to the assembly, we can see that it's now completely broken. And if I move those elements, they are not linked with each other anymore. And so really the issue that's happening here is like the way we do CAD today is we start with sketches. Those sketches define the geometry. So the geometry depends on the sketches. And then the assembly depends on the geometry. And then if you have different versions of assemblies, like it also depends on the same geometry. And so because there's this dependency always on the previous step, it means that if one of those steps is broken, all the rest of the assembly process is going to be broken as well. And if we start thinking of how to automate the assembly process and the version control process of very complex assemblies, we can see that this process like just doesn't work. It's not stable enough to produce repeatable results. So I was trying to find ways to solve this issue, and I decided to look into this idea that is, I would say, inspired by functional programming or maybe forward kinematics, if you're familiar with it in robotics. And so the way it works is that instead of directly defining your geometry by making a sketch at a given place, what we could do is we could define a function that's called the function f that takes an argument and that returns this argument at a given location. And so what you could do, for example, is if you want to draw a point at that location, instead of just like drawing the point and putting some dimensions to put that point at that location, you would just call the function f on the point. And this would basically give you the point at that location. Then what you could do as well is you could actually define this as a higher order function. So it means you could put a function inside the function. So for example, if you have a function that creates a hole, you could put the whole function, we're going to call it like this, inside the function f, and that's basically going to call the whole function here at the location. And then you can also use that to make an assembly, because if you call f on a part, like this, of course you're going to get the part at that location. And so hopefully you can see here that this doesn't require any dependency on the previous step. Because the way it works is like if you want to define a sketch, it only depends on the function f. And if you want to define a geometry, you can also just call a given function. And if you want to define an assembly, same thing, you can just call this function. And so now if we want to change your sketches, your geometry, and your assembly, you can just modify the function f, and it's going to impact all of those without having dependencies between them. So technically, this should make for a more stable way to build CAD and also to automate the way we generate assemblies. Okay, so this is where we start getting into the buggy sections, so please bear with me. So we can call this tool that I built, and it looks like this. So you can see two things here. First, you can see this tree, and this one basically defines how all those functions that we talked about are chained together. And maybe to make this a bit more clear, actually what's going on here is like if you think of the skeleton of a finger, we have a first function that goes from the origin to the first finger section, and then another one to the second one, another one to the third one, etc. And this is kind of how we build this this assembly, and we can essentially like call one of those functions onto another one. So for example, we call f1 onto f2 onto f3 onto a point, for example. And what this will give us is essentially a point at loc 1, which is at the location 2, which is at the location 3. So it really moves that point all the way to the end of a finger, for example. So this is what this tree is showing us. Each one of the path function is one of those patterns that I just talked about. And then we have two different types of functions. We have a part function here. This one just fetches one of the CAD models from Onshape and brings it into a model. And then we also have a point function, and this one just puts a point in 3D space. And so the point function is useful because I can use that to generate all those points that you can see here in the 3D view. And we can actually then publish those points here, for example, when I create geometry. And so this means that now if I was to change any one of those patterns, not only would it update the underlying geometry, but it would also update the assembly in a very stable way. The last thing you can see here is this matrix, and the way this works is that each of those numbers here corresponds to each of those functions here, and at the top here those are the outputs of all the functions, and every time we have a cross, it means that we connect the output of function 2, for example, here to the input of function 4. And so with this interface we can just really quickly chain all those functions together. So for the purpose of this demo, let's try to see if we can kind of automatically add ball bearings at every finger intersection here. So this means we want one on that side, one on the other side, and we want this for every single finger interface to the next section. As you can see, we currently don't have any bearings there. And so the way we can do this is if we come back to our interface here, we're going to be adding a few functions. So the first one that we're going to add is part function, as I said before, to actually get our ball bearing. So we're going to add it like this. It's number 15, as you can see. Then we're going to add a pattern, and this one is going to be a pattern that moves the ball bearing and offset by a given offset in Y, so that we put it in the correct location, so it's slightly offset from the center here of the joint. So we can add that. And then we can add another pattern to actually do a mirror. So to move that ball bearing also to the other side. So I'm doing that here. And you can see that those three functions were also added here now in the tree, but they're not connected to anything. So we can solve that by now switching to graph mode. And now you can see I have a cursor and I can actually move through the tree here. So what I'm going to do is that I'm going to connect the ball bearing to the first pattern. Just going to add a cross here, and now you can see, and now those two have been connected. Then I can connect my pattern to the mirror. I can do that here. And then finally, I can connect the mirror to every single finger section so that we add all those bearings that we actually wanted. And so we're going to add one at the end of the finger, another one here, another one here. And I also want some in the thumb, so I'm going to add one here and I'm going to add one here. There we go. Now, if we look back at our tree, we can see that our ball bearing, as well as the mirror and the pattern, have been added to all those key sections. We can now save that. And then we can build this process again, just like that. And now technically if I reload the model, I zoom in to the joints, yeah, we can see that all those ball bearings, so it's not super obvious, but you can see that the ball bearings have been added to all the relevant finger section, and it's also been done on the thumb here. And so I hope you can see that this way we are essentially able to create very stable assemblies where the function actually defines everything. It defines the geometry, defines the point cloud, and it also defines how the assembly is created. And so another benefit of using this is that if you have to create many variants of an assembly, it's very easy to do that because you just have to change the settings and the parts that you inject in this tree. And so to demonstrate this, I've created this interface where I'm actually generating 9 different versions of the hand, and each one uses different parts. So for example, this is the one we just saw, except that it's in different geometrical configurations. And then we have another one with longer fingers that we can see here, also in the same geometrical configurations. And finally, we have one here with finger sections. I hope this demo showed how using functions can help us have a more stable assembly process and can also help us maintain variants of assemblies. See you next time. Bye.